So now just a few words about mitigating risks. And what we know about mitigating earthquake risks in the normal sort of civil engineering human scale is that predicting seismic events is really very difficult. And it's better to spend your money on engineering and looking to see if buildings and structures like freeway bridges and things like that are strong enough to withstand the main seismic events that you expect in a particular region. So the earthquake summary or the earthquake prediction problem is very difficult to solve, and you can't sort of make human scale predictions too easily. Mine scale seismicity, there are some exceptions, and in some cases that is possible, but still we want to spend, I think, most of the money on support or engineering solutions to make things safer. So support's the first thing that I'll mention there for mitigating risks. So down the bottom, you can see mesh. If you worked underground, you see mesh all over the place. There's a couple different kinds. Some are stretchier than others, able to support more load and more deformation than others. And the other thing, of course, is rock bolts, split sets, um, epoxy bolts, and then cables. And cables are longer than the dimension of the typical drive. So in a 5 by 5 meter drive, you can't put in a 10-meter bolt because it's stiff and straight, but you can put in a 10-meter long a cable bolt because the cables are flexible. You grout them in and that sort of thing. So the support should be designed for dynamic loading. So if a seismic event does come through, the shaking adds to the load. And so there are ways to design for dynamic loading and make the support able to handle the events. The second item there on the mitigating risks sequence is monitoring. So deeper underground mines typically have seismic networks, and the seismologists are able to monitor the state of seismicity, what's going on in good detail. They're able to tell you what sort of events are happening. If there's a bigger one, they can and it's observed in enough stations, they can typically tell you, well, was that a reverse faulting state of stress kind of earthquake, or was it a strike slip, or was it a normal faulting, or does it look like an explosion? Does it look like just a rock burst? Or alternatively, they can tell very well if it was a blast and not a seismic event or a rock burst. So monitoring, and then if there's a change in the sort of background seismicity, in some cases that says to the team, hey, there's a possibility, a higher possibility of a seismic event in the near future, and then you get the equipment and the people out of the area until things calm down and you go back to sort of background. So the next thing that you can do to mitigate the dangers is to do what's known as preconditioning. So two diagrams there. Basically what you do as you're doing your excavations, you drill out quite a ways in front of the excavation where you're planning to go, uh, lay a charge out there, and then blast and cause fractures to happen. And the fractures then slip slightly, reduce the stress or relax some of the stress in the area where you're going to be mining. So then as you mine into the area with the actual excavation, you've relaxed some of the stress. So that's the idea behind preconditioning. And the thing is, it's a little bit hard to tell if it actually works, but in most cases, it is thought to be quite helpful. The other way to do preconditioning is to actually do fracking, what's known as fracking, or pressure up the fluid pressure until it causes new fractures to form out in the area where you're going to be mining. And that's done particularly in the eastern states in Australia, I believe. So that's another possibility for preconditioning. Then the other things you can do, sequencing and backfilling. So backfilling I'll mention first. So it does help to fill in your stopes, makes it a lot safer after they've been mined, and typically the obvious thing is fill them with waste rock or gravel. You can also use something that's a little bit stronger, has a bit of strength, so you can take tailings and put them together with some kind of binder, and sometimes that's called CHF, where there's concrete plus tailings mixed together and then poured into the open stopes after mining. All kinds of procedures involved around that, and a lot of interesting sort of rock mechanics that has to deal with it. Not simple, but probably an important thing to be doing in most mines. Then the top item there, sequencing of the panels where you're stoping, and then allowing time is important. So you can model this using computer modeling techniques of the evolution of the stresses and strains, and come up with beneficial ways to sequence. So if you have a large area that you want to stope, shown by the rectangular prism in the picture, you might choose to mine area 1, then 2, then 3, then 4, then 5, and doing it in that order might be substantially different than sort of progressing evenly from east to west or from one side to the other. So sequencing and backfilling, two important mitigation areas to make things safe underground. Then the other thing is exclusion times and volumes. So we do know that after big blasts or after large seismic events, that there is a time decay. And this comes from a famous Japanese seismologist named Mori, who noticed that the number of aftershocks after a big earthquake decays hyperbolically with time. And as I mentioned, it's also known to be the case pretty much with large blasts underground. So the data on the right shows the number of events. There's a big blast at the vertical green area there on Wednesday, and there's then a number of fairly high magnitude events. Those are the green ones, and then those drop off with time, and you get back to the background, which is the much smaller blue and gray events after a couple of days. And so the strategy here is when you're going to have a big blast that can cause associated seismicity, typically what you'll do is you'll calculate a reasonable amount of time based on your experience with the instrumentation and seismology in the mine. And so you'll exclude people and equipment from the area where big blasts have been while things relax and settle down. And that might take 6 hours, 12 hours, 48 hours, depending on how you tune it up to your particular situation in a particular mining area. So just one other thing to mention, and this is sort of like more for structural geologists than geotechnical engineers, but you might have realized if you're a structural geologist and you're trying to help out the geotechnical and the seismology in your mine site, you probably want to be thinking about what are the biggest faults that could be reactivated or could cause slip events. So remember, part of that is, well, let's have a look. Let's try to figure out what's around. So look at everything. Look at the surface mapping. Look in the pits at the surface. Look underground. Try to figure out how big could faults be. What are their orientations and what are their properties? The other thing to remember is that reactivation in strike-slip mode in the Yilgarn terrain, and that's what a lot of the small seismic events are at depth. That's despite the fact that the Yilgarn is in a reverse faulting state of in situ stress. Reactivation is different than a fault that's always moved the same direction. So I'm showing here some large-scale corrugations in a normal fault on the left. That's from the Basin Range, and there's some oblique slip corrugations in the fault on the right. So reactivating either of these in a strike-slip mode would probably be difficult because the corrugations, you're going to have to fight the corrugations. You may need to break through some of those corrugations to get a nice continuous larger fault surface. So reactivation might be a different game than the situation where you're say going to use a reverse fault that's historically been a reverse fault, and then you're going to reactivate it in say reverse fault mode again. So this is an important thing to consider as a structural geologist, and it might be part of the solution to the problem. So that is pretty much the conclusion of the presentation. Please do get in touch if you have any questions. Happy to be involved in discussions, and love to hear from anybody who has some controversies to add, some comments, really anything. Okay, thanks for listening. Cheers.